Good morning, good afternoon, or good evening. This is now question 5 of the Step 2 2024 paper. Once again, with all of these step questions, you should be having a full attempt yourself before you start looking at any hints, tips, or even solutions. And therefore, you should only be watching this if you've already attempted the question successfully or have spent enough time to really gets sufficiently stuck that you need a hint. And when you do get such a hint from a video like this, you should pause it and try and follow through the hint before watching the entire video. So we now have a question 5 here. This one, to me at least, looks a lot more pleasant. It's talking about ranges, it's talking about algebra and functions, and particularly, which I'm quite intrigued by, which makes the question quite a bit different, is we are restricted to the domain of z. So we're only allowed to input integers into these functions. So really, we're imagining these functions not, or we can't really imagine these functions as an entire curve. Rather, they are just a sequence of distinct dots. So the quadratic functions could look something like that. And therefore, as we're in the integers, talking about their range is going to be a sequence of distinct values as well. So if this was in the real numbers, to show that two things have the same range would simply need to show, in the case of quadratics at least, that their minimum points are the same, so their ranges are both the same. With integer world, though, we need to show that every single integer that one creates, the other creates only those. So enough yabbering, let's actually have a go at the question. We have our two functions, little f1 and capital F1, and we want to show they have the same range. Now, you may have noticed straight away, but there's something clever we can do with f1. Currently, it is in just expanded quadratic form, but if I complete the square, I can rewrite it as n plus 3 squared plus 2, and now that looks almost identical to capital F1. Except now we have the input of n plus 3 rather than f1's normal input of just n. So actually f1 is just a translation by an integer is the important bit, a translation by an integer of f1. So f1 is a translation by, and really we should be really careful which way round we're saying this. I believe if we translate f1 by 3 in the negative direction, we get to f of n plus 3, capital F1, and so little f1 is the other way round, by 3, I'll just say by 3 is of f1, so have the same range. In particular, if we wanted to get a particular output of little f1, we'd simply use 3 less as the input to capital F1 to get the same output. So that, again, step questions do this a lot. That's likely to be a trick that we'll use a couple of times in this question. Part 2. We have another function g1, again with the domain z, defined as so. So g1 of n is n squared minus 2n plus 5. And before I even read the rest of the question, I'm going to guess that a similar trick is going to be needed. Plus 4 there. And I'm going to complete the square straight away. We want to show that the ranges of f1 and g1 have an empty intersection. Well, we could try and put these two things equal to each other. We'll have to use different inputs. Maybe use little n and m as the two inputs and show there's no integers n or m that work. I'm slightly tempted here, again using an idea which is officially outside of the A-level course, is to think about modular arithmetic. Because it looks like here, f1 is always 2 more than a square number, whereas g1 is always 4 more than a square number. So if we can somehow cleverly show that those can't be the same, there's no square number which, no, there's no number which is 2 more than a square number and 4 more than a different square number, then we're all good. And now I'm going back to my other idea of using different letters, because then the two square numbers will differ by 2, and there aren't that many, well, there are no square numbers that differ by 2. Let's go with that one. So let's be clear what we're attempting. So for contradiction, so I'm going to try and find something in both ranges and then show that that's actually impossible. For contradiction, assume there is a n and m in the domain such that f1 of n is equal to g1 of m. And let's see what that implies. So that'll mean n plus 3 squared plus 2 is equal to m minus 1 squared plus 4. So m plus 3 squared minus m minus 1 squared equals 2. So are there two square numbers which differ by 2? Well, if we think about our square numbers 1, 4, 9, 16, etc., they always differ by a odd number. And certainly if we take non-consecutive square numbers, then they differ by more than, well, a lot more than 2. So let's make that comment. Square numbers or square integers differ by at least, well, the smallest is 2 squared minus 1 squared, differ by at least 3. So we have a contradiction here. Thus, the ranges of G1 and F1 don't intersect. We assumed that they do, and then led to a contradiction. There are no square numbers which are close enough together for this condition to hold. Part 3. We have functions f2 and g2 now. Find any integers which lie in the intersection of these ranges. Again, the trick that we've done so far hasn't failed us yet, so I'm going to do the same again. I'm going to write them both in complete the square form. So f2, we get n minus 1 squared minus 7, and I am just mentally in my head re-expanding these out and seeing if they we do get back to the original, and here I believe we have minus 2. And then if I expand that out in my mind, I do get the plus 2 on the end that I wanted. So again, we're looking for things that lie in the intersection of these two ranges. Well, this time, if I were to do the same trick as above, my square numbers will differ by 5. And that is possible. You can have square numbers that differ by 5. So let n, m be in z such that the outputs are equal. So that means that n minus 1 squared minus 7 equals m minus 2 squared minus 2. So then the difference between my square numbers is 5. Now, how can I get two square numbers which differ by 5? Well, from the comment earlier, the difference between consecutive squares is always an odd number. Well, here we've got an odd number, so it's the difference between two consecutive squares. So that can mean that n minus 1 is 9, or n minus 1 squared is 9, and n minus 2 squared is 4. Now, can we get non-consecutive squares that have a difference of 5? No, because the smallest square is 1, which will mean we have to have 6 being a square number. That's not going to work. And as the square numbers get bigger and bigger, they get more and more separated. So we certainly can't go past 4 and 9. Well, this gives us a couple of solutions. So this means n, well, the square root of the 9 plus or minus 3 plus 1, and the m is plus or minus 2 plus 2. So find any integers which lie in the intersection of these two ranges. Well, we want the outputs. These are our inputs. So if I sub any of these numbers back in, and actually it'll be easier to sub that back into F1, we get the overlapping. So 2, and is there another one? If n minus 1 squared equals 9, that's the only option for then subtracting 7. 2 is the only integer in both ranges. And there was actually a lot of different values that could have led to that. We could have had n being 4 or 2, using the plus or minus there. And if I do double check and sub those back in, if I do, let's say 2 squared minus 2 times 2 minus 6, that doesn't seem to give me, oh, it's negative 2, that's why. Yeah, I was subbing that back into the uncompleted square form of f, and I wasn't getting the right answer. If I do sub negative 2 in, I do get a solution of 2. If I sub 4 in, I do get a solution of 2. And then my m values, if I want to be complete, would have been 0 and 4. If I sub 0 in, I certainly get the output of G2 being 2. And if I sub 4 in, the same again. So 2 is the only integer in both ranges. I've done the little mental checks to see to check that I do get 2 in both of those cases. Again, this question hasn't been too unpleasant so far, but as I said at the beginning, this is a kind of question which I would target straight away as a favourite. So part 4. Now this has a weird start. This initial part seems completely unrelated to the rest of the question. We want to show that this expression is always greater than or equal to 0. First instinct is again actually to complete the square. We've got a p squared and a q squared, so I'd quite like to write this as a bracket squared. We know that square brackets are always positive. So this looks almost like p plus q squared, but that would give me 2 lots of PQ, whereas I've only got 1 PQ, so I need to lose one of them. Now this doesn't make me particularly pleased because, well, we've got a positive thing subtract a negative, subtracting something, so that could end up being negative. So not maybe the best choice. So I'm actually going to go back to the idea that the question's been using repeatedly and actually complete the square on this rather than seeing it almost looks like p plus q squared. So completing the square, you'd halve the coefficient of the p, which is a half q. You'd subtract off that thing squared. And now we actually see a much more pleasant expression, because now we have the sum of 2 square things, which is greater than or equal to 0, as p and q are real, and real squares are greater than or equal to 0. Also justifies why we had to say p and q were real. If either of them were complex, then that statement is no longer true. Okay, interesting question. Why is it useful? So finally we have 2 more functions, f3 and g3, both with domains of z. And again, we want to find where their domains intersect. We have cubics this time. Now cubics, is there my first instinct here is we've completed the square every time, and that's been exceptionally useful. Is there a complete the cube formula? Is there something that I can write which can rewrite these as something cubed plus or minus something? Well, in first instinct, yes, maybe. But the leftover, and if you look back to our complete the square of the quadratics, our leftover was always just a constant term, because we used the first 2 terms. Now with complete the cube, we'd use the first 2 terms. We'll use the n cubed and the n squared, but the leftover might be linear, which maybe doesn't help us quite so much. Now, it's the only idea I have right now, so maybe it's worth giving a go. So I'm going to try it. I'm going to write f3 of n, and we're going to try and complete the cube. Now, when we complete the square, we halve the coefficient in front of the n term, and that was because n plus something squared is n squared plus 2an plus a squared, and there's the 2 that we had to deal with. So what's the equivalent idea for complete the cube? Well, if I do try and expand n plus a cubed, either you could do this as a triple bracket or using the binomial theorem, the binomial expansions, we get 3 from Pascal's triangle. So we actually need to divide by 3 for the coefficient. So this is going to look something like n minus 1 cubed. And if I were to expand out n minus 1 cubed, again, easiest and quickest way is with Pascal's triangle, we get that expression. Okay. Well, that's what I have, but I don't want plus 3n minus 1. I want plus 7n. So I need a little bit more. So we need an extra 4n. Now this straight away makes me really pleased because I've got a plus 4n in G3. And then I need to add 1 to cancel out. So now I'm starting to think like part I of the question. Part I of the question, we wrote one of them in terms of the other. Can we do the same here. And we need to be a little bit sneaky with this f3. And I'm going to write this as 4 lots of n minus 1. So I'm going to make both of the n bits look like n minus 1. But now this has a minus 4 on the end. I don't want minus 4, I want plus 1, so I need a plus 5. Well, this now we can say is G3 of n minus 1. But that has a minus 6 on the end, so I need to add 11. Now, was that actually useful? We found a link between these two functions. Maybe it's useful. Maybe it was better, and I'm now starting to think it's probably better to leave it in this form. Because if we're looking at the outputs, well, we want the outputs to be the same. And that final statement hasn't really shown the outputs are the same. Whereas even in the other form, it hasn't. I'm starting to think in this form, if we did the trick which we've done in part 2 and part 3, if we pick an n for one of them and n for the other and find a difference, then maybe we can give a statement for the difference between cube numbers is something. But this term, one will be in n, one will be in m, and that's not particularly helpful. So, what could we do instead? Find integers that lie in the ranges, in the intersection of the ranges of these two functions. Well, certainly now I can think about the function g3 and g3 of n minus 1 plus 11. But then we're choosing different letters. Again, I'm going to run with it and see. So let n and m be integers such that f3 of n is equal to g3 of m. So I'm looking for something which lies in the intersection of the images. So, and I'm actually going to be a little bit sneakier here. I want to make my life slightly easier. So I'm actually going to choose to put n plus 1 in here, which isn't going to make any difference, except when it comes to this here. So that's going to mean that g3 of n plus 11, which is the f3 of n plus 1, is equal to g3 of m. So what we're really looking for is two inputs of g3 whose outputs differ by 11. Helpful? Maybe. So this is saying that 11 is equal to m cubed plus 4m minus 6 minus n cubed plus 4n minus 6. And I'm starting to lose a little bit of faith in this method. It's starting to feel like I could have just put n and m in immediately and got a very similar. Well, no, if I did it immediately, I'll have an n cubed and n cubed and m cubed and n squared and m squared and the linear and potentially constants. If I do this subtraction here, we've got m cubed minus n cubed plus 4. I'm even going to put that in there as well. The numbers cancel. And I'll quite like to use the first part of part 4 somewhere, which currently isn't obvious until, well, another really useful thing to know is if you've got a difference between the same powers, you can factorize And if we factorize this, we do get something familiar. We get that term, that bracket, the p squared plus pq plus q squared. So this thing here is always greater than or equal to 0. Now we don't know really anything about m minus n in terms of at least its size, but maybe we can do some more. So another trick which I'm employing here is, because we're in the world of integers, we can actually think about the factors of numbers. So we get this, and the only way to factorize 11, which is what we've done here, we've written it as a product of two brackets, the only way to factorize 11 is with 1 and 11, or negative 1 and negative 11, but we know that this bracket here is now greater than or equal to 4, as 11 has factors plus or minus 1 plus or minus 11. This is actually forcing m squared plus mn plus n squared plus 4 to be equal to 11. Only that's the only factor that's bigger than or equal to 4. And if that term's 11, then m minus n has to be equal to 1. Okay, we're getting somewhere. We now really have we actually have simultaneous equations now between the m and the n. So m is n plus 1, and this one we can at least simplify to equal 7. Now I'm debating how the best way to solve this would be. I can't think of any nicer approach than just to sub the m in and simplify. So this is going to be n squared plus n squared plus n squared equals 7. And if we simplify that, we've got 3n squared plus 3n and minus 6. This can be simplified down. So we get n plus 2, n minus 1. So n is negative 2, or n equals 1, with corresponding solutions. M is negative 1, or m is 2. Okay, so if there's something in the overlap, then it's only with these values. So let's find these things. So let's, going back to what the definition of these were, G3 of negative 1, or G3 was negative 1 cubed plus 4 times negative 1 minus 6 is negative 11, which should be the same as if I subbed negative 2 into F3, which was negative 8 minus, if I sub negative 2 in, that's minus 12 minus 14. That's quite a lot further away than negative 11. So what has gone wrong? We have, that's why, because my input here isn't n, it's n plus 1. So this should be the same as f of negative 2 plus 1, which is negative 1, and then that's negative 1 minus 3 minus 7, which is indeed negative 11. So negative 11 is in both ranges, and if I do G3 of the other solution, G3 of 2, so that's 2 cubed plus 4 times 2 minus 6, which gives me 10. That should be the same as F3 of 1 plus 1. 2 cubed is 8 minus 12 plus 14, again, is 10. So, thus, 10 and negative 11 are the only integers in both ranges. To me, at least, that was a very satisfying question. Managed to use a lot of different integer equation tricks of factorizing a number and looking at its factors, tricks of complete the square. Turned out this entire question was clever uses of complete the square, even a clever use of complete the cube. Not fully convinced that the complete the cube was necessary. If you'd done it in another way, then this factorization trick that we ended up finding would have been a bit more difficult to find. But probably possible without that. But it's really useful in these hard step questions to take whatever hint the question is giving you and to run with it. All right. If you're carrying on looking at these step questions, good luck, and hopefully some more of these would start to be uploaded soon.